Mhm. Okay, I was struggling to share my screen, but I made it. Good morning, good afternoon, good evening to everybody here. Welcome to the, I don't know how many webinar it is now, organized by the MIA Specialist Group. So my name is Elena Turfs. I'm the current chair of the MIA Specialist Group, and I will just take 2 minutes of your time to give a short introduction before we, of course, I pass the ball to the actual speakers who you came to listen to. So who are we? We are for those who don't know, the MIA Specialist Group. We are a specialist group focused on modeling and integrated assessments, of which I'm currently the chair, supported by Saba Daneshkar as vice chair, and a whole big management committee of other very active people that are making this webinar and other activities happen. So MIA, what we do? Well, in very general words, we focus we try to bring people from all kind of parts of the water sector, consultant research companies, institutions together to think along and to create activities to stimulate the use of models and computing tools for better understanding, better management and optimization of water systems. So really looking at integrated assessment, how can we look at the water sector as a whole, and how can we use models and other tools and other digital tools to make this happen. What kind of activities do we do? Well, we have task groups to start with. So specific groups focusing really on a specific topic and see like how can we consolidate the knowledge that is in this topic. We have 2 active ones now on membrane bioreactor modeling and control, and one on good modeling practice. In gray, you see a lot of historical ones that have finished and that each published a very extensive and nice scientific and technical reports. So if you're interested, you can always find these on the website of IWA. We have a number of working groups also, 4 active ones at the moment on integrated urban water systems, computational fluid dynamics, good modeling practice, and hybrid modeling. If you're interested in knowing more on any of these working groups, you can find more info on Iowa Connects on LinkedIn page. You can always reach out to Mia. If you have any ideas to start your own task group or working group on a topic that you think is super interesting to get people together to work on, feel free to reach out and we can see how we can support these ideas. We organize we support the organization of 2 specialist conferences, WRRF and WaterMatex. And of course, we organize webinars as you are here. Maybe just one specific mention here for those who don't know, the meeting is being recorded. All of our webinars are being recorded and they can be looked at again later on on our MIA YouTube channel. So you can also find all of our old webinars there if you missed one and are interested to catch up. Also here, if you have your own idea for a topic for a webinar, feel free to reach out and we can see how we can support the organization. We have recently, or in the last months, decided, it has been decided by the community where the next WRRF and WaterMatex conferences will be held. So put this in your agenda. The next Water Resource Recovery Modeling Seminar will be next year, end of June, July 2026 in Spain, close to Barcelona, organized by Juan Antonio Baeza and Paloma Grau. And the next WaterMatex conference will be the year after in Sète in France, organized by Jean-Philippe Steyer and Gabriel Capson-Tojo from INRAE. So I'm sure that the call for abstracts will be for WRRF will be coming somewhere in the next months. That's it. That I just want to mention as an introduction. If you want to know more, you can find us on Iowa Connects, on LinkedIn, and of course through the open website of the MIA Specialist Group. Okay, I will pass the word on to Luis Coraminas, who will introduce the topic of today.
Yeah, hello everyone. So my name is Luis Coraminas. I'm in charge of coordinating the group of webinars within MIA. And I'm going to introduce the webinar today. So water resource recovery facilities of sensors. It all starts with process knowledge. And we have two great speakers. So we have Leif Rieger from Jacobs and John Kopp from Remodal. And both, probably you know them, they are excellent modelers and experts in data quality. And they have prepared this session today with an example on N2O emissions modeling. There will be two sessions, two presentations, followed by Q&A. So feel free to post your questions in the Q&A and in the Q&A application that you have in the Zoom meeting, and we will be able to sort your questions and organize how we answer them. So with no further words, I pass the word into John, that you can start with the first presentation.
Yes, thank you. Let's do that here. Okay. Good morning, everyone. So Live is going to talk this morning about some N2O modeling, and I'm going to first start us off though with a project that I did a few years ago on trying to understand the behavior of a wastewater treatment plant that I could not intuitively understand. And it led me back to the sewer and to trying to understand the behavior of the sewer on any given day. And so today we're going to talk about the soft sensor that I developed for the sewer, and which then helped me understand the behavior of that treatment plant. And as the title of this seminar suggested, all of this work had very little to do with math and a lot to do with just intuitively sitting back and thinking about what might be going on and trying to develop a soft sensor around what might be going on. There are lots of mathematical tools out there, and Live's going to talk about one that leads you to that conclusion. But I think it's also very important to understand that you can get to this same conclusion by just stepping back for a second and thinking about what's going on. So we'll start with what the issue was, and then I'll go through the methodology for the model development. I'll show you what I did for the model development, and then we'll show some results. So a fairly straightforward presentation this morning. Here we go. Okay, so here was the problem. So the problem is that this is a fairly large wastewater treatment plant. But the behavior during dry weather is not consistent. So it's a highly automated treatment plant. It serves several 100,000 people. And yet on any given day, I could never predict the behavior of the nitrification from Tuesday to Wednesday, even though the weather was identical, the flows were identical, and yet the treatment plant seemed to operate differently, and I could never really understand this. And this is a treatment plant that I've been working on for, I don't know, maybe 20 odd years, I think was the first time that we were ever in this plant. And it's always been a bit of an unknown for me at this particular plant. So we had these high flow events, which was fine. I mean, we all know about first flush events, and but we needed to be able to predict them, and we needed to predict the severity of what was going to happen given a flow, such that we would have storm events of a certain size, and they would have a completely different impact on the treatment plant even though the flow was the same and everything else was seemingly the same. So we wanted to try to understand that. And so was there another explanation? So is there an explanation for that could be used to mechanistically describe what was going on and why the treatment plant was behaving differently? So what we could do, and this seems to be the latest approach, which I will be perfectly honest, I don't honestly subscribe to, but is we could just take all this data and put it in a big pot, swirl it around, and see what comes out. Okay. But I think that for me, the better approach is, well, let's just step back and see what actually might be happening. From a mechanistic point of view, I don't find wastewater treatment plant particularly complicated. And so when weird things happen, it's usually possible to somehow figure out what was going on at that particular time, and to then use that to describe a behavior that you hadn't captured in the model, and to adjust your model accordingly so that it captures that behavior. So we have to think back about, okay, what is driving any kind of process behavior? Why does nitrification change on at any given moment in the day? And sure, is it hydraulics? Sure, absolutely. Hydraulics will have an impact on how the plant behaves. Movement of solids, nitrification behavior, retention times, all of that stuff. And if we looked in this particular case, we know that the hydraulics can potentially have an impact, but we have subsequent dry weather days, sunny days, where I'm actually at the plant watching this treatment plant, and it behaves completely differently on two seemingly identical days from a hydraulic point of view. Is it operations? Well, it could be. You could have a overzealous operator out there who's tweaking valves or doing, making a change, recording it maybe in a logbook, but not really understanding what the impact is. And that's definitely a possibility. However, when I looked at the particular behavior of this plant, I couldn't justify, or I couldn't figure out a mass flow of material within the process itself that would explain the behavior in the effluent. So meaning that even if I turned centrifuges on and I did all kinds of weird things with recycles, and I couldn't really get the plant to fail the way the plant was failing on it any given day. So could it be control? And it absolutely can be control. I had a treatment plant a few years back where it was failing its ammonia consent every single day. And we went in and did a model, and the model clearly showed that there was a delay in the response of the aeration controller. And the owner of the plant swore up and down that there was no issue and blah, blah. And we said, well, I'm telling you that something weird is going on. They went and actually looked at the PLC code and found that there was a hard-coded 30-minute delay in the aeration controller. And I said to them, well, if you take that 30-minute delay out, I'm pretty sure your treatment plant will be fine. And sure enough, they took that out, and it was absolutely flatlined on ammonia. So these things do happen. And but in this particular case, the controller behavior had been unchanged like for years. So as I said, I've been there for years, and no one touches the DO controllers, and no one was touching anything. And yet still we were getting this strange behavior from one day to the next. So the next most plausible explanation is the wastewater itself. So we know that the wastewater drives the process behavior, it drives the ammonia behavior, it drives the solids production, it drives everything. And so if it's the wastewater, then I had to start thinking about, okay, well, why would the sewage composition vary? Like, if we think about it, do people's behavior actually change from one day to the next? I've been to treatment plants where I've done diurnal sampling, you know, years apart, and the diurnal pattern is identical. So we know from experience that people's behavior on average doesn't really change all that much. Yes, it changes us slightly from day to day, maybe. And yes, there's behavior on the weekend that's not exactly the same as it might be on a weekday. But for the most part, people's behavior on any given day doesn't really change. And similarly, industrial processes and industrial wastewater doesn't actually change all that much. Sure, you may have a process that, you know, every Tuesday they do something and so on and so forth. But on average, over the course of a regular week, these things don't really change very much. And so the question was, okay, well, if we still make the assumption that it's the wastewater, how is it possible to create a soft sensor, or to come up with a model of the sewer, a very simple model of the sewer, that might be able to predict these changes in influent that I would need in order to describe this you know, unpredictable behavior of the treatment plant at the moment. So for my whole career, okay, which is now spanning over 30 years, I have always sort of up until this point subscribed to the concept that the characterization is fixed, that people don't change and that industry doesn't change. And so that if you have developed a characterization of your influent, you can hold that more or less fixed. And that you get the variable nature of your influent through the storm input, which is obviously variable. So you have a domestic load, which is consistent from day to day. And then on top of that, you add the variable nature of your influent can be described with some kind of storm input. So it might be variable flows. It might be, you can describe your first flush event with the storm, and so on and so forth. And so this has been, you know, for me, quite successful. I mean, it's quite useful in terms of design questions. Most of the work that I do, of course, is design or control or optimization. And for the most part, this sort of simplification has worked. The model is very good at predicting these things, and it's very good at pointing to areas of control that would benefit the treatment plant. So the biggest part about approaching this is this idea of generating a variable input. So the number of presentations that I've been to over the years where they talked about that they had to vary the characterization over time to get the behavior that they wanted, and I'm thinking to myself, okay, that's fine. I understand that you need to have this variable input in order to get the behavior of your treatment plant right. But then how do you predict that variable input? Just because you've been able to predict the behavior in the past by dynamically changing the input, how do you use that going forward to be able to then use that model for prediction? Because you're now all of a sudden going to have to predict variable changes in the influent characterization, which is obviously far more difficult to do unless you have some kind of understanding or mechanism in which you're basing it on. So, so this approach, in the last several projects that I've done, I've started looking at, you know, is this a generalized problem? And it turns out that from my perspective, it is sort of a generalized problem. That this approach works, but it's not, if you're getting into the fine details, it's not ideal, because it really misses quite a bit of the variable nature of the influent, and therefore misses some of the behavior. And so if we accept the assumption that people in industry don't change, okay, from a day to day, we have these consistent flows and consistent loads from the domestic component. And we have an inferable rain. I mean, we know what a dry day looks like at the treatment plant. And by difference, we can infer how much rain hit the catchment on at any given moment in time. Okay, but we need a variable flow and variable loads at the treatment plant. So somewhere in here, we have something going on that is changing that consistency of the inputs to something variable in the output. And the question is, okay, so why or how is that influent composition changing? And can those changes be mechanistically explained or predicted? Because if those can be explained or predicted, then we can use our model to predict the future. And then that variable influent composition is now predictable, and therefore we can generate artificial storms for the future, and we can assess what we believe is going to be the loads and the real influent variable influent that's going to hit the treatment plant. So this all came about because I was sitting at the treatment plant one day, and I was watching the SCADA screen, and it was not raining at the treatment plant. Okay, so it was a cloudy day, but it was not raining. And I watched the effluent ammonia at this treatment plant start to rise, and it was in fault within a couple of hours. And I walked downstairs to the operators and I said, "Are you watching this screen?" And they looked at me and said, "Why? What's going on?" I said, "Because your plant is about to fail its consent." And there was absolutely no indication at the treatment plant that something was going wrong out there. And post-storm, so the next couple of days, I took a look at what was required to have caused this very large treatment plant to fail in such a short order of time. And they received almost a full day's load of ammonia in a couple of hours. And I then had to phone around some of the catchment people and find out what happened. And it turned out that there was a very large rainstorm in another part of the catchment that we never experienced at the treatment plant. So I started thinking about this. I thought, okay, this can't be explained by, up until this point, we had all been reasonably convinced that the centrifuges at this treatment plant were the issue, and that the operation of the centrifuges was causing a huge ammonia load to the front end of these plants at inopportune moments in time. But this event, sitting there and witnessing this event, clearly showed me that it had absolutely nothing to do with the centrifuges and that everything was coming in the sewer. And so I started thinking, okay, well, what can we do? What is possible? And I started thinking about this idea that, what if deposition and resuspension are a function of the flow in the sewer state, meaning that, let's argue that you have a dry period of time, and on any given dry day, there is a net deposition of material in the sewer. And then as the flows in the day change, and as rain events, small or large, come down the sewer, you end up resuspending some of that material that's in the sewer. And that material in the sewer digests a little bit. So you have this deposition during dry days. You have a net deposition of material in the sewer. It starts to rain, and you have a resuspension of that material, which then eventually hits the treatment plant. And I thought, well, how can I sort of mechanistically describe this? And could I predict variations in daily diurnal wastewater strength? So could this explain how I get different, even on dry weather flow days, that I get different loads I seemingly get different loads to the treatment plant? And would it also explain the first flush events, such that the same storm might have a completely different effect depending on what day that storm hit the treatment plant. Okay. And so that was the premise on which I started to think about the soft sensor. And so if we look at what I was just talking about, is we have this idea of deposition and resuspension happening based on flow. So if we take a dry weather day, and which is, you know, more or less represented by this green line. It says mass, but it's not. So this mass is the green line at the bottom is the mass. Sorry, the blue line in the bottom is the mass deposited by the domestic and industrial load. Okay, and overnight when the flow is low, you get more deposition. So you get more of that material just settling out in the sewer and not being pushed. Then as the flow increases during the day in the morning, some of that material that was deposited overnight gets pushed to the treatment plant. So you get not only the domestic that was generated in the morning, but you also get some more domestic load pushed to the treatment plant, because it's taken some of that overnight load with it. And then in the afternoon, same thing. As the flow goes up and down, you get some resuspension and some deposition. So if it rains, then what happens to the underlying sort of intuitive model that I'm thinking about developing is that you get this resuspension. So it's whether it's raining overnight or raining during the day, you have more force on that material in the sewer, and you're scrubbing some of that material into the treatment plant, and therefore you're getting this variable influent. And because that material is digesting in the sewer, you're also able to then model this variable characterization. So now all of a sudden your ammonia to TKN ratio is changing, and your solids is changing, and your VFA portion of your incoming COD is also changing, depending on how long that material has been sitting in the sewer. So if that stuff has been sitting in the sewer for 2 weeks digesting away, you're going to have it's going to contain a whole bunch more ammonia that's trapped and released as soon as a big storm comes through. You're going to have more volatile fatty acids in that material, and that kind of thing happens. And so the nice thing about the conceptual idea of this model is that it satisfies all of the ideas that are required in order to predict the behavior of the treatment plant. So what do you end up with at the end of the day? What does the model look like? In the model, this is basically a representation of the model. I don't know if the colors come through perfectly for you people, but basically it's a three-dimensional model where if the sewer state is full, such that it is it doesn't it can't, no more material can be deposited in the sewer, a low flow continues to slough material to the treatment plant. And if the sewer is empty, then you get deposition at the same flow. So, and then similarly at the bottom of this figure, if the sewer is empty, it requires a high flow to flush it clean. But if it's full, you're going to resuspend an awful lot of material to the treatment plant. So and so what does it sort of conceptually look like from over time? So if this is just a conceptual picture, but if you have this shows like 4 dry days, say, to start this period of time, and you see that the sewer state is filling up, and you're getting this net deposition and some resuspension every day, but you're getting a net deposition. And then it rains. And when it rains, and depending on where you are the sewer state, what the sewer state is, it will resuspend a mass of material. And how much mass of material is a function of how full the sewer is at that particular time. And then the sewer state goes back to dry weather and the sewer state starts to rise again. And so, as I said before, you get a different behavior with the same storm depending on how many dry days you've had prior to the storm event ever hitting. So it's a relatively simple model. The only to run the model and to this is about a soft sensor, right? I mean, this seminar is about a soft sensor, and the output from the soft sensor has only one input, and that's the flow. So, and that flow can be measured at the inlet to the treatment plant. You don't need the flow anywhere else. This model actually, the calibration of this model was surprisingly good, and required only the influent flow to generate that idea of this variable nature of the influent. To calibrate the model, yes, we had to do some, we already had the data for, we knew the diurnal fractions for the flows. We knew the concentration diurnals on a dry day. We had done a bunch of concentration work to try to understand a regular dry day. And we all, as part of that, we also knew the solubles. So what this ends up doing is that from a soft sensor point of view, our only input is flow, and treatment plants have a raw flow. And so from only using the flow, we are able to calculate what we believe to be is an estimate of the strength of the sewage and the characterization of that sewage that's entering the treatment plant. And so what did we do? So we were able, in this case, to show or to model or to develop a tool that that predicted that the flow alone was sufficient to allow for a different influent characterization over time. So we assume the same domestic load to the sewer every single day. That doesn't change. And simply through a change in the flow, we were able to then have a variable input to the treatment plant over time. And using that variable input over time, we were able to predict this variable nature of the nitrification at the treatment plant over time, even on subsequent dry days. So the deposited material changes over time, as I said, because it's digesting and sitting there in the sewer digesting, which is really nice because it satisfies one of the issues that we were having, and that is this idea of variable, VFA, and like we were getting variable denitrification behavior and variable nitrification behavior, and we couldn't really explain it. Okay. So the results from the model. So here's what we see. So the top graph shows the flows. Okay, so the orange is the calculated storm flow. The yellow is the dry weather flow. So that's the assumed dry weather pattern underneath. The addition of the orange and the yellow would be the measured flow at the inlet to the treatment plant. And then if we look at the middle graph, we see the particulate and the soluble curves. So the predicted particulate component of the influent sewage and the predicted soluble component of the influent sewage. And we see how they vary differently. So what the model allows it to do is that these two things now are varying independent of one another. And if we look at the third graph at the bottom, this is just the ratio of the soluble to particulate material. And again, we have a fixed characterization of the domestic sewage entering the sewer, and yet entering the treatment plant, we are able to model a variable soluble to particulate ratio, which then gives us this variable characterization that we need to model the variable nature of the treatment plant. So we looked at ammonia. We looked at the behavior of the model in relation to the estimated ammonia at the inlet to the treatment plant. Just to make a long story short, we estimated the influent ammonia from some sensors in the treatment plant a little bit further downstream. And what we see here is that the dark yellow line is the model predicted influent ammonia, and the thin line is the estimated ammonia based on the sensors from the treatment plant. And you can see how the sewer model that we've developed actually tracks fairly well the variable nature of that influent ammonia. And again, it's really important for you to understand that the domestic portion load to the sewer did not change. It was identical every single day. And yet we're still able to predict this variable nature at the inlet of the treatment plant. So how is this valuable? Well, it only requires, this model, once calibrated, only requires one input. And I think that that's a very valuable, when you have a model which really only requires one input and is able to predict a whole bunch of things, I think that's quite valuable. The base characterization of that domestic wastewater was constant and held constant for the entire time. And yet we were able to model variable daily masses to the treatment plant, and a variable characterization was also achieved. Okay, so this is not math-based. This is straight up just intuitively modeled. It's mechanistically based and intuitively modeled. Okay, and as a result of all of this work, we were able to model that variable ASP behavior in the nitrification. So thank you very much. And I'll pass it over to Live, who can take over for me.
Okay. Seems to work. Okay, thanks, John. I really like John's work. So I think everyone doing that type of modeling at one point thought about the drivers of the influent dynamics, but that is a really neat model. What I actually would love to see is the first option John mentioned that didn't really do is throw all the data in one pot and see what a data-driven model or machine learning model would come up with, right? So that was just as a comparison purely based on John's vast experience, and you see it works. What would a data-driven model do? Okay, to my presentation again. So I also talk about why process knowledge is so important. And what we did is we developed a structured approach to develop a data-driven model with diagnostics to help us improving the model step by step by identifying bad data, for example, or missing information, right? And that is where we got guidance where we should add process understanding. Okay, so I start with the presenting the team, and that is not so much to give them credit, so they clearly deserve that, but also highlighting how important that is to work together as a team and get different domain expertise into your model. So I start with Emma. So she's our team lead, an excellent process expert, of course, but mainly she brought in a deep understanding or state of the knowledge on N2O, right? So very important because it's all about N2O. And as we know, it's quite tricky to fully understand what the drivers are. On the other side, we had Ivan Miletic. So he's our data analytics expert. And he basically coded up all the methods, so the models and the diagnostic from scratch. So no third-party software, no package used. It's really developed code from scratch. What might be even more important is the contribution of Jesus and Lucas. So these were the people on the ground. So that luckily for us, there were parallel projects where we as Jacobs had people on the ground with a very deep understanding of the ongoing processes, of the problems faced. And also, and that is quite tricky, they had a direct connection to the operators, right? And getting that operator information into the model is not that trivial, right? So, and these two were basically the main source of that information. And again, so that is the key information and also the most difficult information to get in. Then we had Joe Green, so he was our client advisor. And that is also important that you involve your client. So we are consultants, right? So we have to do that very structured and fast, right? So we have to stay within budget and time. So Joe was involved from the beginning, and that made sure that any missing information was organized, but also that we delivered into a scope so that they could improve operation. My role was mainly to translate between the different experts, right? So that is also a key role, I would say, because they're all talking different languages, right? And that it's very important if you want to get that into one model, which requires using the same language, the model language, you have to be able to translate all that expertise into that language. Okay, so just a little bit about context. I think I don't have to go into details here. N2O emissions contribute significantly to greenhouse gas emissions, and with that to global warming. And N2O has about a factor of 300 times that of CO2. Both of the plants were in Ontario. There is a special situation that the energy is mainly generated by nuclear and hydropower, which means that for a wastewater treatment plant, about 80% can easily come from N2O emissions, right? So to improve the greenhouse gas footprint, it's very important to understand that N2O is actually one essential factor to deal with. And we see that throughout Ontario, throughout Canada and North America, that more and more facilities are aware of N2O problematics. And there are also more and more measurement campaigns and sensors installed. So what we wanted to do in this project, we realized that it's challenging with all the data. And again, so we had parallel projects, we collected a lot of data. How do you extract specific information on N2O emissions, right? And so what are the impacting factors driving N2O formation or accumulation? And of course, if you want to mitigate, you also have to understand what are the control handles you have to mitigate or reduce N2O emissions. Just one upfront note, we focused on N2O measurements in the liquid phase. Of course, we understand that there is a stripping process to N2O emissions, but we didn't have any data. So our focus clearly was from the beginning that we try to understand formation of N2O in the liquid phase. So the solution we targeted was basically to develop a diagnostic tool based on a hybrid model. So the main model is data-driven, but then we use diagnostics to add process knowledge. And thanks for the little line there. Very nice. Okay, so what we wanted to understand is why do N2O emissions occur, and what can we do to reduce N2O emissions. What we then developed is a very structured way to deal with a huge amount of data and driving model development. And this is a methodology which can be applied to N2O, but to any other project problem as well, right? So we start with the, can I remove that? I cannot see my own slides here, so let me see if I can move that away. Yeah, that's better. So the first step is, of course, to obtain all the raw data. So this is, of course, SCADA data. So in our case, high resolution data, because N2O is very dynamic, data from the lab. And then we go into the tricky part, right? So this is information on operation, right? So that is, for example, an event log, right? It might be stored set points, but then there's also a lot of data which is not available in digital form, which is operator insights. And that is, again, where Jesus and Lucas played a very important role to collect that information. And we used the model and the diagnostics to actually figure out where to look, right? So there's so much information somewhere, but you typically don't know what is important to drive the model. So the next step is data ingestion. That is mainly to get all the data into one database, checking timestamp issues so that you have consecutive data points, the classic problems with zeros and not a numbers, and in general missing values, daylight saving time, that kind of thing. And then we go into data cleaning. So of course, we went through all the event logs and we knew when, for example, sensors were cleaned, right? So at these plants, there was a log. Maybe they didn't collect every single one, but we made sure that we have that information. We also wanted to remove data with poor quality. So you can do that based on statistical tests, but also on operator insights, right? And how you feed that information to the model is not that trivial, and we use that process to do that. Then it's about data pre-processing. So we basically were running the model, and then remove variables with limited correlation, for example. And then we analyze where the model was fitting very well, and other periods where we couldn't get the model to explain the data, basically, right? And we developed these diagnostics to be pointed to these things. Again, so these are huge amounts of data, and of course, a true expert would be able to spend a month or two looking through all the data and then coming up with something, but we didn't have that time, right? So just upfront. So the first model building that was mainly driven by the need to code up things took a few weeks. The second one, Duffin Creek, we did in one single week, right? And I would say what we got out is very impressive. And keep in mind, we did that in one single week. Then we want to add our process knowledge. So if we know something, right? So for example, calculating the load out of concentration and flow helps the model quite a bit, right? So as John pointed out, the flow has an impact in terms of hydraulics, but also in terms of load, right? So that's kind of a double booking, right? And what this does, upfront calculation of loads, means that you put more weight on the flow in the model. Yeah. We also calculated control errors, right? So there were a lot of presentations in Toronto at the World Water Congress indicating that bad aeration control leads to N2O peaks, right? And we looked into that and said, yeah, so if that's an issue, then we should tell the model that there's an error. So typically you would feed just the DO concentration, but not necessarily the set point. And what we are doing is we are telling the model that there is a known correlation between the set point and the measured value, right? And we also tried, at least for Duffin Creek, to add data from a mechanistic model, right? So with the idea that even if roughly calculated model, there should be some dynamics that the data-driven model can use. Yeah. Then we went into model construction, so build and train or retrain the model. And then the important thing is you need to have criteria, and we used the goodness of fit measure I explain in a second. And then also very important is to visualize the model outputs, right? So again, so we use these tools to discuss. So we have to be able to easily communicate among the experts and define what the next model iteration should be, right? So visualization is key for the discussions and the exchange of knowledge and experience on the N2O emission drivers. So the diagnostics, they help you getting information to the surface, right? So just running the model, you said, oh, it looks nicer than before. That's not good enough, right? So we want to be able to see which variables are driving at that peak, what is causing that peak, right? So very important, the diagnostics are driving our model iterations. So then again, so we want to have pointers where information is not available yet, or there's not enough information in the data yet to explain the N2O dynamics. So and then we iterate a couple of times. In fact, that iteration, there are a lot of iterations there. And so if you have a reliable model, then you can start analyzing, using the diagnostics to increase your insights into what is driving N2O formation. And a step further, so that's clearly not the focus of that project here. A step further is to find ways to mitigate N2O emissions. And again, there was, except the two N2O sensors, there was no additional measuring campaign. So that was all standard data available at the plants from the lab and from the SCADA system, right? So nothing on top. I'm not saying you shouldn't do that, but again, so we had very limited time and budget, and we had to use what was already available. So, and that whole process, using the diagnostics to identify where information is missing, I think that differentiates that approach from pure machine learning, where you just use a data dump, throw it in, and say, oh, the model will sort it out. Yeah. And I saw so many of these machine learning studies where I think, I don't like that. And I think the results confirm that this is the way forward. To model construction, this is also very important. That's a language question in the end. You have to make sure that your data analyst understands what you want to get out, right? So in our case, why did that specific N2O peak occur? Or what variables were driving that peak. And if you can identify that, so that let's say the model follows that peak, and you analyze what drove that peak, then you gain insight. Yeah. And of course, we want to know which variables can be changed to prevent that peak as well. So there's a clear difference, right? So that it's not clearly that you list a couple of variables, and if you would change them, then the peak would change. So it's a correlation, but not a cause-effect relationship necessarily. Yeah, so you have to keep in mind and not overinterpret what is happening. So we use the model and the diagnostics to guide our work, right? So that is very important. A reliable model, or if the model is explaining most of the data, then you have insights, right? So you gain insights, but then you can also think about using it as a forecaster, where you can optimize to mitigate NTO emissions. But that's stepwise, right? So this work here, so there is hopefully a follow-up project where we look into mitigation, but this one is mainly to better understand the drivers. Okay, so the modeling methodology, you want the model to explain the correlation between inputs and of course, the outputs. And then what most people look into is the correlation from inputs to outputs. So why is it important to also understand the correlation between the inputs, only the inputs and only the outputs? It's quality control. You want to be able to see how consistent the inputs are. So, for example, to detect sensor failures, and also for the outputs, you want to see, is that still in the range you're expecting and where you have trained the model for? I would say the algorithm itself is not that important. What you want is a robust one, and I used this paper from Louis here to highlight that PLS, so that's the algorithm Ivan used, projection to latent structures, is very established, and it's known to be very robust. And that is more important to us than a fancy new algorithm coming up with slightly better correlation, maybe. You also have to make sure that the model is capable of managing missing values, right? So what is happening if suddenly there is no point, right? So you have to have a way to make sure that if you feed data and there's one point missing or multiple points missing, that you are able to bridge that, right? So you cannot allow the model to fail because there's some data missing. Very important is assessing input data quality. So we did that a lot through iterations, but if you run that model online later on, you have to make sure that you have ways to identify failing input data, for example. And then, of course, the model should be able to handle the nonlinearities of a biological system in our case. Automation is very important because that is required if you iterate several times. And Ivan is currently further automating with the goal that in the end we could have a discussion of all the involved experts, and we could run the model, so rebuild, retrain the model on the fly and see what's coming out, right? So right now we had meetings. Then Ivan went back, was running all the models with some level of automation. And then we had another meeting and went through the data. So a lot of iterations and discussions. Okay, so highlighting again, the focus is not data fitting, right? So of course, in the end, you want to have a reliable and trustworthy model. But interestingly, the diagnostics, even of the early models showed or pointed to the right contributors to NO2 peaks, N2O peaks. So that's quite important, right? So you always measure the success in terms of how good the fit is. And again, if you want to use the model, you still want that. But the diagnostics were with let's say, a not fully developed model as well. Yeah. So what we use as the main driver is percent of sums of squares explained. So basically how good the model can explain the data in percent. It's something very easy to understand, I believe. What is important is that we do that for the inputs and the outputs. So the main focus, and later on in the tables, I only show sums of squares explained for y, so the target, right? But you also want to know how consistent the input data is, right? So that is also very important. That makes the model robust. And if you are switching from model development into applying the model, that may become the most important criteria, right? So that you make sure that your model is still describing the data coming in, right? But also being able to identify any issues with your input data. Okay, so a couple more diagnostics. We use the variable importance plot on the right, and it ranks variables for information content. And we also use that to set a threshold to remove variables with information where variables where the information content is limited. So that is increasing the robustness of the model if you focus on the key drivers. And then, so if you start analyzing specific peaks, we used something we call contribution plots. So on the right, what you see is you have all the variables we are using, and that is for one single data point. That plot shows which variable contributed the most, right? So that is a really cool tool to analyze what is driving a peak, right? So analyzing the dynamic of the data. And then this is something in this project, we did mainly manual, but also important is to identify periods of poor fit, right? And you can run that through a control chart and you identify this is where the model fits really nicely, but here not, right? And that is very important, as I will show in the results. Okay, so let's jump into the two case studies. We have Elmira, so that is a plant in Ontario, rather small plant, serves about 12,000 people. It's a project where the conventional activated sludge plant was extended or upgraded by an MABR module or modules. We also had two Unisense liquid phase N2O sensors downstream of the MABR tank. At that point, plant, we had a scatter data resolution of about 5 minutes, plus lab data. And because it's a small plant, the lab data was rather limited. The second plant, Duffin Creek, that's a big plant, right? So that is about 1.3 million people it serves. So that is one of the big plants in Ontario. It's not conventional activated sludge plant, and we focused on what is called stage 3, so 6 parallel tanks, and we measured in one of them, right? So luckily, we were involved for Elmira in the MABR commissioning or design commissioning. And for Duffin Creek, there are all kinds of projects in parallel. Lucas and I are doing a parallel study on aeration control, right? So we really had insights into a lot of dynamics already, collected a lot of high resolution data, in this case, 1 minute data. So this is also important because N2O is highly dynamic, right? So it's an intermediate, and if it pops up, then typically the time constants are very small, right? So having high resolution data is actually a requirement to build a proper model here. That is what we realized running the first model, I think was 15-minute data. So different plans, different variables, but the same model structure was applied here. Again, so the first plant, we spent a few weeks. Duffin Creek, we did the whole study in 1 single week. Yeah. Okay, so let's start with Elmira. So what you see in that table are the main iterations. I have to admit, in between, we tweaked the model a little bit. So there are more than just the 6 listed here. But these are the main steps, right? So, and what I wanted to see is what is happening. So the base model is you just dump the data and let the model building process sort it out, right? And you can see that we started with a percent of some square for the target variable was 43.8. The next step, we looked through the event logs and when probes were cleaned and calibrated and basically removed unrelated variables. For example, the data dump included data from the second train, right? So we said, no. So we focus on one. So that's a direct correlation. So let's get rid of all the variables in there. So if you have a data dump and don't go through, you get all kinds of things which are not related or should not even be fed to the model because it's not connected at all. So we did all that, and you see that the goodness of fit measure jumped up by about 5%, right? So then we started to prune the data even more. So there were some operational changes in the beginning, and we realized that one of the probes was moved around, right? So it's pretty difficult if you try to model a moving target, right? And then the biggest change was when we took out a chunk of data, we identified where the model was just not fitting at all. And you see the improvement by 20%, right? So that is a major improvement. And this is basically also what I focus here. It's not enough time to go through all the iterations and all the findings, but I focus on that one. So you see model 3, and you can see with your bare eye that the first part is not fitting really well, whereas the rest of the data is actually following. So if you zoom in, it follows the diurnal pattern very, very exactly. So what that means here is there is something happening we couldn't really explain, or in other words, we didn't feed certain information to the model. And we discussed that, and in the end, it was obvious, just to say that up front. But a data-driven model has no guidance what is important information. A mechanistic model, you have unit processes and you have defined inputs and geometry of these. So you're kind of guided. You have to provide these parameters and information to build the model. In a data-driven model, you don't have that. And I remember we had a call in the morning and Jesus was saying, oh, I really don't know what that could be. And then we had another call in the afternoon. He said, I'm so sorry. I completely missed that. So what was happening is that this was the period where the MABR was first not commissioned yet. And then the commissioning of the MABR started, and then, you know, it's a startup, so it doesn't really work. And they had issues with the DO probes and controls and all kinds of commission things, right? So we didn't feed that information to the model. So how can the model fit the data if key information, right? So adding an MABR was, so we didn't tap the model, right? So it's pretty obvious to me that this is a key. MABRs are having a big impact on N2O. So our idea would be to actually say, well, use the oxygen content of the off gas to feed the performance of the MABR to the data-driven model. And that will give you a lot of additional information for the model on N2O. So key here is you have to understand what operational information needs to be fed to the model. And again, a data-driven model, that's not that trivial. So a little step back now. So this is operational information, right? So you have really well documented information on operation. So that is set point stored in your historian, right? So you still have to feed that to the model, but it's already there, stored in a high resolution, hopefully, and it's available in electronic format. So then you have somewhat documented information. So this is the famous or infamous logbook entries. So on sensor cleaning or change of operation, something like that, right? And this is very important because you want to get these peaks out, right? So if you clean a DO probe, there's a spike in DO, which is not happening in the reactor, right? It's just the cleaning process. And you want to get that data out before you feed that to the model, because the model has to react to these peaks, right? Standard operation procedures, hopefully they are followed. Process control narratives, I know they are never up to date, but it gives you a lot of information on how the plant should be operated. And then there's the most difficult part is undocumented or anecdotal information, right? So you could say, you should ignore that, but unfortunately you cannot, right? So, and that the difficult thing is, and that is true for mechanistic or data-driven or hybrid models, how do you know that there is something you should know, right? And we used the diagnostics to guide us, right? And point us, there is something. And then you can go out and say, do you know what happened on that day? And then at times an operator will say, yeah, so there was something, right? So that pump broke and we fixed it, but well, right? So we didn't bother putting that into the logbook. So very important to understand your sources of information and then finding ways to get that into a format you can feed the model, right? And that includes you somehow need to quantify if you want to send that directly, or it means you are taking data out, right? Okay, so next step, this is now analyzing peaks, right? So you see on the right-hand side, that orange rectangular here, there, we only analyze one data point. So we are analyzing the highest peak, but we plot that frame there, right? And what you can see, it's the ranked variables contributing to that N2O peak. Again, so it's just one data point, right? And what you can see is 2 of them point to aeration, right? So let's not look into the other ones, right? So we have done that partly, or maybe we didn't have enough time, but basically let's focus on aeration. For the second one, same thing, right? So this is basically, so the first one is right after the MABR tank. At times it was even in the unaerated tanks, but so that is more, or it's closer to unaerated tanks. Let's put it like that. The second sensor is in always aerated tanks, right? So what you see is that all of them, or nearly all of them, point to aeration, right? So from the data we have, so it's identified by the model and our diagnostics. So I'm not saying aeration is the only trigger, but our analysis showed that aeration is the main contributor, right? And one of the actions the plant, so we recommended to the plant, is to work and improve the aeration controls, right? Okay, so next study, so that is Duffin Creek, same thing, a couple more iterations here. And we basically went through the same steps. Here we said we actually want to know which every data set contributes. So we actually added the LIMS data later on. And you see that the LIMS data, so the lab data, improved our goodness of fit measure by 6-7%. Right, so a major improvement, right? So just adding LIMS data. So the nice thing here is you can quantify how the model develops with every step, right? So that is something we want to learn from to speed up our analysis. One additional thing, so that's model 7. We actually decided we had a roughly calibrated model, right? So we are looking into aeration, and we know the model was not calibrated in detail. But the thought process was that we mainly want to need dynamics, right? So the first step in the data-driven models is you normalize and mean center the data, right? So if you're hitting that ammonia peak exactly or not is of no importance to the model, right? So we thought if we say add some more ammonia and nitrite information, or the information on the dynamics, that may make a difference, right? So I wouldn't, so we didn't really spend enough time there, but what you see is it's a meager 1% improvement. What that means is that most of the information we need to explain the N2O data is already available, right? So I'm not saying that you cannot improve the model, or if you would have proper ammonia data, so dynamics, variation of ammonia, which we don't, right? That could help explain the data even better. But the biggest step, and we identified that again, so I show that with data in a second, the biggest step, so really whatever, 20% jump in goodness or fit, was from identifying and removing a faulty set of data from one of the DO sensors, right? And you could argue, I should have maintained that better, and it was obvious and you should have seen that, but fact is there's so much data that you typically cannot do everything you want, right? So what we focus on here is that step here. Okay, so this is model 7, and you see that there is a certain data set where we just didn't fit the model. So we went through and said, okay, so this is very clear if you zoom into the data that something is not right, something is missing. So hypothesis was missing information or faulty data. So that triggered that we said focused on that period of time and took that out, and the model accuracy jumped up, right? So it improved the model predictions for the remaining data. Yeah. So analyzing, so that's, some could argue, well, if you remove all your outliers, of course, the model fits perfectly. But we use that to guide our analysis, right? And what we figured out then, and that was not available to us before, is that for one of the N2O sensors, the temperature sensor failed, right? So the light blue one is temperature of the first sensor, and the dark blue one was of the second N2O sensor. These things happen, right? And of course, you should have said, well, somebody should have looked at that, right? But as you know, that data is typically not fed to the SCADA system, and somehow that was overlooked for quite some time, as you can see, right? So very important message here, right? So we try to recover that data and recalculate, but yeah, so that is not in that slide deck here. So clearly faulty data, and if you are trying to model something which is wrong, it's clear that you don't get a very good model fit. So important here is that the diagnostics guided us in identifying that, right? So that means that we got insights by being directed, there is something, let's figure it out. And it started a whole analysis. So Lucas had to go through all kinds of data, and then he came back and said, I found it, right? So that guidance is very important. Okay, so another one here. So this is sensor 1 here. Again, right? So there are, basically we have cut out that faulty data set, and now we are trying to understand what is driving the peaks there. So again, 2 of them. So that sensor 1 is also closer to the underrated tanks. So 2-point duration still, right? Again, so that is our identification. It doesn't mean that this is the only reason that N2O accumulation or formation happens. But we basically use that, sorry, so we use that DO control error here and thought, well, let's see what the correlation is. So we plotted it. And you see in blue, that is the measured N2O, and in red, it's the predicted. And you see, yeah, well, these peaks are not really linked, but clearly you see the DO control error in orange. So that there it's, you see that there is a correlation, right? Okay. If you look at the DO itself and the DO set point in green, you would say, oh, over-aeration triggers N2O, right? So that could be one conclusion. So the problem is that actually the DO control error is based on the DO probe at the very end of that tank, so in end of pass 3, whereas the N2O sensor sits in the middle of the second pass, right? So basically it would mean that the DO error downstream impacts upstream N2O emissions, right? So that doesn't sound right, right? So what I want to highlight with these slides is you have to be careful, right? So that is clearly something we overlooked. We should have taken that variable out, right? So you have to be careful with the cause effect interpretation. Yeah, so I just wanted to build the chain of argumentation, but basically that should not be possible. Okay, so then we thought, well, let's look into cell 3. So this is where, so that's the DO control error in cell 3, where the N2O sensor was located. And you see, shoot, that correlation is gone, right? So there is nothing. But if you look at cell 2, so the aeration zone right in front, which could have an impact on N2O, you see that that correlation is back, and actually you see that the peaks are showing a higher correlation. So keep in mind that the red, the predicted, is still based mainly on the DO error in cell 4, right? So we didn't change the model here. But you can see that, well, there's something different, right? And you see it's still higher than the DO set point. So you clearly could see that there is a correlation, right? So it's not cause effect. There is a correlation between DO control error and N2O emissions. So now you can question, is cell 4 control error the right model input? Probably not, right? So should we feed the control error in cell 2? Yeah, we may. But if I look at that result, right, so that's just 6 days here. But you could also argue that maybe it should be a moving average, and it's the variation of the DO which is upsetting the whole process, right? So keep in mind, N2O is an intermediate, so something was messed up in the pathway. So maybe it's the variation, right? Okay, so another example, that is sensor 2. And right, so similar to Elmira, sensor 2, every single of the top 5 ranked variables contributing to that one single data point to aeration. Yeah? Again, so we are feeding a certain set of data, but because we are fitting the measured N2O very well, you could argue the information in that data set is sufficient to describe N2O. Okay, so basically, so let's briefly go back. So what I'm looking into first is the air valve opening in cell 4 and the air valve opening in cell 3. So you see in dark blue, this is the N2O measured, and you see the valve positions as soon as they're hitting the maximum bound, there's a spike in N2O, right? And that is very clear, and it's quite immediate going up, and it's quite immediate going back to low levels when aeration works again, right? So if you look at the DO itself, I think that is probably easier to understand. You see that DO drops to nearly 0, right? So that it's impacting the process for sure. So the drop in DO clearly correlates with N2O peaks, right? So the first set showed that rather high DO peaks correlate with N2O, and this one now shows that a drop in DO correlates with N2O peaks. Yeah, so, right, so what is it, right? So what I personally find really amazing is how the shape of that N2O peak looks, right? And if I compare the measured N2O with the predicted, so measured in blue, predicted in red, and then I show the DO control error, right? And you can, I think it's pretty amazing how well the model tracks N2O during low periods, but then it immediately reacts to it as well, right? So what does that tell us, right? So the interesting thing for me during the peaks, you see that the measured N2O spikes but then drops again, right? So DO is still 0 or near 0. So it looks like kind of adaptation, right? And you see that maybe that's a new state, right? So that organism is in. So is there maybe some adaptation happening, right? Because you see that every single time, right? So DO drops, N2O spikes, DO stays low, but somehow it comes down and seems to get to a new state. Maybe if that would take longer, it would go back completely. But let's not overdo the interpretation here. So you could formulate, I'm not saying that's the reason, but you could formulate that N2O accumulation triggered by a sudden exposure to an atypical condition will trigger that N2O, right? So what we see here in the data is maybe a partial adoption to a new state. And what is also interesting is as soon as DO comes back up to where it typically is, N2O drops to low values again, right? So what can we do now? So that's a hypothesis, right? So the model clearly pointed to that, and now we can further analyze, right? So I would say what the model tells me is that we capture all the external information quite well, but what is happening if there is something happening inside the organisms? And of course, we don't have any information on that, right? So are there ways to kind of measure the internal state of an organism, right? And there are some sensors around. So maybe it's time to look for something else. So maybe it's not that high ammonia causes this or low DO causes that. So maybe it's an adaptation problem, right? So again, so I'm not saying that's the solution to everything, but our goal was to be guided in that analysis, right? And I think the model did that very well. And we have a new hypothesis to look into, right? Okay, so just highlighting sensor 1, that's a zoomed in just to show a little bit of the dynamics. You see that the model tracks the ups and downs very well. So look at the concentration here. And then these two peaks are not fully covered, but as we discussed, that might be because we are using the DO error from the end to predict N2O upstream, right? So I'm sure we can improve that. For the second sensor, I found that amazing, right? So you could argue, well, it's reacting too much to the variation of DO, right? So that's the DO error. And you see this was a period where there was high oscillation of variation controls. But you see clearly that it follows the pattern exactly without being able yet to describe the whatever process that is. So I call that adaptation, but there is something we are missing. We are not feeding that information to the model yet. Yeah. Conclusions, again, so this was fast. We did that in one single week for Duffin Creek, right? And we are automating more. So we are confident that we can analyze data sets very, very quickly if we have the right expertise in the team. Yeah. Key was really the diagnostics. And again, we use that to guide our work. The success really depends on the multidisciplinary team, right? So if you don't have people understanding the plan, you will fail. Yeah. So we were in a very lucky position. And I would say that our models, again, put together in a week, reflect the N2O trends very, very well, right? Was clearly highlighting where we have to look deeper into what is happening and what information we need to add to that. Next step, so there is hopefully a follow-up project where we first identify what control handles do we have, right? So knowing that something contributes is not enough, right? So you have to have a control handle. You have to be able to change whatever a DO set point or sludge retention time or something, right? So we are planning to do experimental design. So we will artificially change these control handles or the values of the control handles and then see how the plant reacts. And then if that is reflected in the model already, if not, we need to refine that model and train that model so that we can use that. And then basically we expect that there will be quite a number of control handles to optimize together. So important is to have an optimizer on top that it is running online and so on. And important for us was to apply the model so important would be, so if you switch from model building to applying models, important is to apply model self-diagnostics, right? So the model has to tell you when it doesn't fit the data anymore, and that is inputs and outputs. Yeah. Okay, I'm done and open to any questions you may have.
Okay. Thanks for that, Live. We'll just we've run over time here a little bit. We've got a few things. I had one quick question for you, and there was one question in the chat for you as well. But it's not clear to me how you decide what is important. Like you showed one graph about with a threshold number. And how do you know where to put that number? Could you maybe expand on how you know where to put that line?
So in this case, we used the threshold predefined, but you could also argue you look at the shape of that curve, right? So this is overall, right? So that is the whole data set. So that's the training data set. And you need to cut off something where you have very limited information content, right? So it's so that's in difference to the diagnostics where you analyze later on to analyze what variables contribute the most to one single data point, right? It's kind of a way to increase model robustness, that you don't feed too many things and overfit the model.
Can I comment on that as well? Do you mind?
Sure.
Go ahead.
Okay.
Sure.
Yeah. So we set the limit based on kind of like a nominal impact of those VIPs. They're sorted by size, as you saw, and then we look for we scale them so that you get like a median level impact per variable, and then distributed that across the coefficients. So in some sense, you could say that this is like a set in a Bonferroni kind of a method for setting up the limit. So in jargon, that's what you might say, but it's basically looking at what we expect each variable to contribute in a uniform sense, and then seeing that as a threshold. And that comes strictly from the coefficients themselves after the model is fitted. There's nothing arbitrarily set up beforehand to define that limit. The limit comes from the model fitting, so to speak. Yeah.
Okay. And Ivan, you and I have discussed this before, and I'm good with this approach. I have one last question, because we are over time. I have one
Yeah,
more
go.
question, and this is a issue for me, is that how, okay, I sat in on a PhD committee meeting. I was recently graduated from my PhD, and I sat in on somebody else's committee meeting, and this person had done a whole whack of work on ASM1, and this is going back obviously a few years, and their conclusion in this committee meeting was that yield, if your sludge production didn't fit your model prediction, that you should be adjusting the yield. And to me, that is like just not the correct approach. And the fear I have with these, with sort of mathematical approaches like this, is that you will end up starting to focus on things that you shouldn't be focusing on, but mathematically are pointing you in that direction. So how does this approach ensure that you don't start fiddling with the yield, a number that we know an awful lot about and a number that we understand and we have a lot of data to support, to fit your model, when in fact you should be actually searching somewhere else for the answer. So if you guys could comment on that, that would be nice.
Yeah. Okay. So the first thing is that there's no presupposed structure in these kinds of models. At least not in the sense that you have in mechanistic models. So you're not coming with a set of equations that are going to be fitted in the sense of fitting some differential equations. You're looking at correlations among the data. Okay, what you hope is that the contributions and those VIP plots and that they do show you clustering or grouping. Maybe clustering is not the right word, but grouping is maybe a better way to put it. Is that they're going to group together and say, these variables that are related to DO may be significant, or these other ones that are related to something else in the process, or maybe heat transfer or temperature or whatever it is, that they're going to group together. Okay, the method itself is not going to be able to tell you don't adjust concentrations, adjust the feed of your chemical instead. I don't think it can tell you that, but it should be able to group the variables together so that you can make with some knowledge of the process or some basic chemical engineering of which variables should be used as handles to adjust. But I don't think that the method itself is going to inherently tell you don't touch output concentrations versus controller set points.
Right.
Yeah.
Okay.
I think that's fair to say. So to your point and to what Live was also suggesting is that with that multidisciplinary team that he presented, I personally, and I've done this for like going on 30 years as well, I personally have had the best success with applying these kinds of machine learning or data-driven models is when I involve people that know the process in scrutinizing and helping to develop the model. Without that, I think you're kind of dangling out in space a bit. That's my personal opinion.
Okay, very good, Ivan. Thanks very much for that. I think that's a ideal way to end, to be honest, with that last sentence. So basically, we need you cannot do these in a vacuum, and that you need some domain knowledge, or with the addition of domain knowledge, you are going to end up with a better result.
Yeah, and you hope the model cooperates with you and kind of confirms your opinion about the domain. That's I would add to that.
Okay, thank you everyone for joining. We are over time, so I'm gonna cut this off now. But thank you again, and I apologize for not getting to some of the questions. If the people with the questions want to email me directly, please do, and we will certainly try to get you back an answer. Okay, thank you everyone for joining, and we'll see you all at another time, I'm quite certain. Take care.
Excellent, thank you.